Let us look at laws of sets. Commutative laws. A union B is equal to B union A. Now, how do we prove this? Suppose X is in A union B. What does that mean? It means X is in A or X is in B. In either case, X is in B union A, which implies A union B is a subset of B union A. Conversely, suppose X is in B union A, then X is in B or X is in A. In either case, X is in A union B. Therefore, B union A is a subset of A union B. So, here we saw A union B is a subset of B union A, and here we have B union A is a subset of A union B. So, since each is a subset of the other, that means they are both equal. So, A union B is equal to B union A. Now, let's look at the same thing with respect to intersection. A intersection B is equal to B intersection A. So, suppose X is in A intersection B. Then X is in A and X is in B. That means it is there in both A and B. Since it is in both, X is in B intersection A, which implies A intersection B is a subset of B intersection A. And by symmetry, the converse is also true. That is, B intersection A is a subset of A intersection B. Thus, A intersection B and B intersection A are both subsets of each other. Therefore, A intersection B is equal to B intersection A. Now, overall proof may appear trivial, but focus on the techniques used. To prove equality, prove that both are subsets of each other. And we can use symmetry to prove the converse. Now let's look at associative laws. A union B union C is equal to A union B union C. So again we follow the same procedure. Suppose X is in A union B union C. That implies that X is in A or X is in B union C. Now if X is in B union C, that means X is in B or X is in C. That means X is in A or B or C. In any case, X is in A union B, union C. Hence, A union B union C is a subset of A union B, union C. Now, suppose X is in A union B, union C. Then X is in A union B or X is in C. Now, if X is in A union B, then X is in A or X is in B. That means X is in A or B or C. Thus, A union B union C is a subset of A union B union C. Therefore, because they are both subsets of each other, we can say A union B union C is equal to A union B union C. So this was associativity with respect to union. Now intersection. A intersection B intersection C is equal to A intersection B intersection C. Same. Suppose X is in A intersection B intersection C. then X is in A and X is in B intersection C. Now, if X is in B intersection C, then X is in B and X is in C. That means X is in A, B and C. So X is in A intersection B, and since X is in C, X is in A intersection B intersection C. Therefore, A intersection B intersection C is a subset of A intersection B intersection C. Now, suppose X is in A intersection B intersection C. Then X is in A intersection B and X is in C. So X is in A and X is in B and X is in C. Hence, X is in A and X is in B intersection C. Therefore, X is in A intersection B intersection C. Thus, A intersection B intersection C is a subset of A intersection B intersection C. So, they are both subsets of each other. Since each is a subset of the other, we can say A intersection B intersection C is equal to A intersection B intersection C. That was associative loss. Then we have idempotent loss. A union A is equal to A and A intersection A is equal to A. Pretty straightforward. These follow immediately from the definitions of union and intersections. We have identity loss. A union empty set is equal to empty set union A is equal to A. Now again, how to prove that? Suppose X is in A union empty set. Then X is in A or X is in the empty set. But no element belongs to empty set. So X has to be in A. Thus A union empty set is a subset of A. Conversely, suppose X is in A, then X is in A union empty set. Thus A is a subset of A union empty set. Therefore, because A union empty set is a subset of A and A is a subset of A union empty set, they are subsets of each other. So A union empty set is equal to A. Now what about intersection? A intersection U is equal to U intersection A is equal to A. Now, if you try to visualize it with a Venn diagram, immediately you will know the truthfulness of this statement. But if we have to prove it, we would go something like this. Suppose X is in A intersection U. Then X is in A and X is in U. So X is in A, because if it is in A, it is also there in U. Thus, A intersection U is a subset of A. Conversely, suppose X is in A. Since U contains all elements under consideration, X is in U. Therefore, X is in A intersection U. Thus, A is a subset of A intersection U. So again, we have shown that they are in subsets of each other. So therefore, A intersection U is equal to A. And by symmetry, U intersection A is equal to A. Then we have null loss. A union U is equal to U union A is equal to U. And A intersection empty set is equal to empty set. These follow directly from the definitions of universal set and empty set. Then we have distributive laws. A intersection B union C. So here this will be equal to A intersection B union A intersection C. So what are we doing here? We are distributing this intersection over union. So distribution of intersection over union. A union B intersection C is equal to A union B intersection A union C. So this is distribution of union over intersection. We can actually go through the proof in the same manner what we have been doing till now. Then we have absorption law. A union A intersection B is equal to A. So A intersection B means what? What is common to both A and B? That means A intersection B elements are there in A. So that means A. A intersection A union B is equal to A. Then we have complement clause. A union A prime. Remember complement we saw in the previous session? That means A union elements those that are not in A but they are there in the universal set. So if we take the union of these two, we get the universal set. A intersection A prime is equal to empty set. Now this, think carefully. We have A which has some elements. A prime is all those elements which are not there in A. So which means the intersection will be an empty set. Then we have involution law. A prime of prime is equal to A. So if you take the complement twice, you get back the original set. Then we have De Morgan's laws. A union B prime. That means all those elements which are not there in A union B is equal to all those elements which are not in A intersection all those elements which are not in B. And A intersection B prime is equal to A prime union B prime. So we take the intersection of A and B, and prime means what? Complement is all those elements which are not there in the intersection of A and B. And similarly, A prime is all those elements which are not in A union all those elements which are not there in B. Now, the algebra of sets closely mirrors the algebra of logical statements. Union corresponds to or, intersection to and complement to not. So that was a set of laws about sets. That's it for now. Bye.